so last Friday we did the lab, and now Gene and I learned a lot. I know things didn't go that smoothly, but you know, it's actually better when it doesn't go smoothly. So yeah, and we're gonna edit the handout to help. I want to thank you guys for your comments. Okay, so we're doing a problem set today. It's the first Newton's laws chapter. First dynamics chapter. Okay? Okay, there's some conceptual questions first. First one is 3. There's the diagram there. Hopefully you've got it somewhere. There are these 4 situations here. There's a block on some frictionless surface, this is the top view, and there are forces exerted on this block. Okay? It's on a horizontal surface. Gravity is irrelevant. Okay? And we're asked if the force magnitudes, you can't play around with the directions are given, but if you can play around with the magnitude, you can play around the magnitudes anyway, whatever you want to do. If they're chosen properly, in what situation is it possible that the block is stationary, that's part A, and part B is moving with constant velocity? So what's the first thing that you pick up on in this problem? A and B. A is stationary, we want the block to not be moving, and B, moving with constant velocity. Is there any difference? No, the forces have to vanish. So the answers to A and B have to be the same. So there's really only one close one. Right, that's the first one. Corresponds to zero acceleration. Zero velocity is a special case of constant velocity. So we've got to have the net force equal to 0. And if you look at that first one there, the first one looks like this. There's some force here and there's some force going off like that. Can we have 0 net force? No way, because we can have these are x and y directions here. We can have no net force in the x direction. This component balance that, but what about in the y direction? We're stuck. The only way you can have no acceleration here is if the y component is 0, which equals 0. That's not fair. Okay, so 1's no good. What about 2? Oh yeah. So 2 has forces going. So if the magnitudes are the same, there'll be no acceleration. What about 3? Well, if you look at 3, chart diagram. At this point, you guys know to bring in something so you can. I could have. With extra work, I could have put them in here. Maybe I should have done that. I didn't. Anyway, 3 is no way. There's now, so something like this. We're stuck. We're going to have a net force in the y direction. There'll be acceleration in the y direction. What about 4? 4 is similar to 3, but we're flipping the pure y component. And we will do quantitative problem like this today. Something similar to this. Gee,
Is your microphone turned on?
yeah, I'm pretty sure it's turned on. I'm sure. Yeah, it's
Okay, just want to make sure.
the little bar is moving when I speak.
Okay, good. Sorry to interrupt you. Keep going.
So what about this? Can I get 0 net force? Yeah, we just have to have the x component here balance that, and we have to have the y component balance that. And the x and y components are independent here. We can freely choose an x component and a y component. So this is possible to have no acceleration. So the answer is 1 and 4. Excuse me, 2 and 4. Okay, any questions? Simple conceptual problem. Now we go to one that takes a little bit of thought, and this is famous. You guys are too young to probably know about this, but this is a true instance, a very long stated problem. I encourage you to read it through carefully. This really happened, as you can tell right from the beginning. I just checked it out on Wikipedia. Over 100 people died and over 200 were injured. It was the worst structural disaster before 9/11 for the Twin Towers. Okay, so we got a lot of attention. And here's the idea. There are these walkways, balconies, in this newly built hotel here. And here's a balcony, okay? And they had too many people on there. But it wasn't that there were too many people. It was the design was revised, okay, as I'll explain to you, and that was the problem, okay? So here's the idea. We've got these balconies here. So there's like 3 different floors. And they're supported by these threaded rod here. And we have an example of beefy threaded rod, but it's too long for me to carry into class. But we're going to cut off a length, right, Gene? But if you guys want to see it, let me know. I'll take you to the demo room, so show it to you gladly. So we got some heavy-duty thread rod here. And these are big nuts, okay? And you can see the idea is that we're going to support this balcony. And here's the total mass of the balcony, including the mass of the actual bare balcony plus the people on it. Okay, all that's important is the total mass. And we're going to assume it's the same here. This was the original design, right? And it was designed to handle, so many people, right? And there was a margin of safety, right? And where it would break would be in the threads of the rod and the nuts. That's where it would break. So, question here. What's going to be the tension? What does each of these balconies have to support here? Well, you can see if we draw a force diagram, sketch just a force diagram for, let's say, this one down here. We've got this mass M. There's going to be weight mg. And what do we have counteracting that? Well, we have these 2 tension forces here. So if you like, we can do this like, we can write it like this if you want. I kind of compacted it here. Each pair of nuts and threads must support mg, okay? So maybe this is a better way of writing it. We have to have 2. So this is the pair here. Okay, what about here? It's the same thing, right? If we draw the force diagram, you can see we're going to get the same thing. This has to be, we have some tension force in here. And that has to be half of, each of these tensions have to be half mg. We're drawing the forces on the mass here, and similarly here. The problem with this design is that it's hard to construct this. You've got to, the textbook says it's impossible. I don't think that's right. I could be wrong, but if you're going to imagine constructing this, these are big balconies, right? You're going to have to put the first one in here, thread this nut all the way up there, then put the next one. It would be very difficult to construct. So they did a redesign here, and I don't know the details of who was responsible for this. But anyway, when you design this, you're going to have a nice safety margin based on the tension in there, each pair being mg. So here was the redesign here in order to more easily put this thing together. So now you just have to have, shortened threaded rod here. You can imagine attaching the first one up here, and then you bring up the next one and attach it. This can be readily done, construction-wise. Here's the problem. Here's what they failed to realize. And this is not obvious. I always have to stop and think about this. Let's look at the tensions in here, okay? Let's start at it's best to start at the bottom. So this is just what we had before. So this is going to look just like that. This pair has to support mg. But now look when you focus your attention on here. You can see that now, in addition to those 2 forces, we now have exerted here let's hold on.
So we have the mg, we have these two, that's new. That's what differs from there. We have these two going down, and their total is mg. So now, this is going to look confusing. We now have, I guess the one way of looking at it is we now have 2 mg here. So we're going to have to double these. So what we have here is the tension in here, and here I put the value right here, it has to be 2 mg. It's mg because of this, and then you got a total of mg there. It's actually, once you see it, it's simple, right? So this is good, and it just keeps climbing. Next, this right here is going to have to support 3 mg. And that was evidently beyond the margin of safety for these people that were packed on there, you know. Maybe there were more people than were specified. I don't know the details, but it collapsed. Okay.
God bless you for saying I was too young to remember that.
Pardon me?
God bless you for saying I was too young to remember that.
Okay, so some of you apparently know about this. You heard about it. Okay. Yeah, I remember it well. It was just, and there's video. You know, it was a big opening ceremony or something. So there, just looking on the internet, I didn't want to look at the video. I just looked at Wikipedia. Any questions about that? Okay, so this is the first Newton's law. We're doing the simple stuff here, all right? Now those are the conceptual questions. Now we're going to get into some quantitative stuff. And we're going to be able to do a lot more complicated problems, but you want to make sure you get the simple problems here. This looks complicated if you look at the solution, but it's not. Here's the idea. There are 3 astronauts with jet packs or whatever, jet backpacks, pushing this little asteroid. And so here's the essential physics of what's going on. The body has a mass 100 kilograms. There's one force here due to one astronaut, one here, one here. So all the information we need to know is in that diagram. We can forget about the asteroid, the astronauts. This is the essential physics, right? And we're going to call this the x direction, this the y direction. And an obvious thing to ask here is what's the acceleration? And that's going to be dictated by the net force. We're going to divide the net force by the mass to get the acceleration. And the simplest, there are different ways of doing this. The simplest is to use components. That's even though sometimes it can be a little longer, you're typically less likely to make a mistake because you don't have to think as much, basically. I don't know if I should say that, but I think it's true. Okay. So here's the idea. We've got our forces here. Let's look at the total force and the net force in the x direction. So I'm going from 1, 2, and 3. This contributes 32 newtons times the cosine of 30 degrees. That's going to be the x component for that force. This force is purely in the x direction, so I just write down the 55. This is all in newtons. And finally here, it's going to be this force magnitude times the cosine of 60. So you punch this in and you get 103 newtons in the x direction. What about the y direction? Are these going to balance? Nope, they're not going to balance. Which one's going to win? Can you see? You don't need to calculate. I'm just saying qualitatively. This has greater magnitude and it's got a greater angle. So there's going to be an imbalance of force in the y direction, in the downward direction. And then the math will tell us precisely what that is. Now we take 32 times the sine of the angle. That gives us this component. And now I've explicitly put in the minus sign. I know it's going to be negative. So I take 41 newtons times the sine of 60. If you don't want to do it this way, there's another way you can do it. There's always another way, right? In this case, you can think of the angle as being negative. Okay, if you want to think of this as being negative, then you would write plus 41 times the sine, and you're going to get the same, it's going to be negative. Okay, so there's 2 ways you can do it. So we get a number here, it's negative. And now, Newton's second law holds along any direction. So along the x direction here, we've got to have the net force in the x direction is the mass times the acceleration in the x direction. So we can get the x component of the acceleration here. It's just the x force divided by the mass. We've got that. We get this, 0.86 meters per second squared. In the y direction, very similar, but you want to, of course, be careful here. You know, this is negative. We ended up with a net negative force. Oh, I should have pointed that out, as we expected here, because this has greater magnitude and the angle's greater. This beats out that, so we've got a negative component here. So we have a negative acceleration in the y direction. And now we can finally, if we want to write the acceleration in component form, we can use unit vectors. And this is an explicit, you know, solution to the problem in components. Now we're asked to take this one step further. Suppose you care about the magnitude of the acceleration and the direction. Well, you see the right triangle here? You know that the magnitude is going to be the square root of the sum of the squares by Pythagoras. We got this net force here pointing like this. It's got a positive x component. I guess it's more like this. It's got a positive x component, negative y component. I get the magnitude by squaring this. It's a right triangle, squaring that, add them together, take the square root. That's the magnitude. And now the direction, the tangent of the angle here is going to be, you know, the opposite over the adjacent, right? So it's the inverse tangent of the y component divided by the x, as we've seen many times before. If I just go merrily along and punch this in, I happen to get the right. I think calculators, at least mine, and I think we've talked about this before. It's going to happen to give you the right answer here, but you always have to check. Remember, because another possibility for this angle here is the angle pointing. So this points at minus 10.5 degrees, right? And that's right. But another possibility. Whoa. Another possibility for the inverse tangent is 180 degrees from that. And there's no way you can, well, without a lot of trouble, there's no way you can code that in. It is possible, okay? In fact, I've written computer programs where I've had to code that in before. I've completely forgotten about that. It is possible, it takes a lot of work. Most people just say, they think about it. They look, is it reasonable? Is this reasonable? You know, an angle like that, yeah, it's reasonable. If you'd gotten an angle here, that's crazy, right? This thing's got to accelerate in the forward direction here, not the back. Not the, you know, it's going to be accelerating somewhere down here, not up here. Okay, any questions about that one? Okay, 13. Oh, the salami problem. All right, this is a good problem. This is classic, classic problem. So, and I was surprised, you know, it's a classic problem, it's been around forever, and they missed something in the wording. The situation is, the first situation is we've got this salami here that's suspended so here's the salami, okay? And it's got some mass, or did I call it? Yeah, some mass in. This is a spring scale, calibrated in newtons, okay? Like you saw, like that little one you saw when we did a demo. And we're in a gravitational field of the Earth. Okay, and the first problem is, what's the tension? What does the scale read? What is the reading on the scale? What the scale is going to read is that the tension in this line here. When we talked about the definition of tension, you can imagine you've got a cord or a rod or something like that, and you want to know the tension. You can imagine cutting out a little section here and putting in a little spring scale. That reading is going to give you the tension. That's what's being done here. But there's an assumption. What is it? Oh, not in this part. Damn. Okay. we're not going to change the problem if we imagine attaching the top of this. We can get rid of this, right, and we just need to attach that, okay? So this is accurate. So the tension here, the reading on the scale, which will be the tension, or I guess it's here. The tension, which is the reading of the scale, is going to be just m times g. We take the mass divided by g. Okay, so that's fine. There's no problem there. That's fine. Now let's go to the next situation. The next situation is this. So we have a pulley here. So there's the salami, and now the spring scale is here. Okay, what's the reading going to be? Now here's where they should have said something. We're making the assumption here that the mass of the spring scale is small compared to the mass of salami. Because otherwise this is, well, this is going to sag, for example, and that'll increase the tension in there. So we want to neglect that. We want to neglect that in this case. Okay. So, what's the reading? Well, if it's not obvious to you, just think force diagram here. What's the tension in here? It's got to be mg. And that just gets transmitted, as we discussed, around here. But then, what about this over here? Well, again, you can imagine that's not there. You can imagine that this is attached right there. And there is a force. This exerts a force on that. Otherwise, this would move. Okay, it's going to be equal and opposite to the tension force here. But we don't. When we look at a spring scale, we don't care. The fact that you're supporting a spring scale at a point here, you're somehow supporting it here. There is going to be a force here. But the reading, we imagine this to be fixed, very typical case. And here's, what you care about here is this tension, this force going down. What it's going to read is that. So the answer to the question here is it's going to read the same. All right? It's going to read the same, just because for an ideal pulley, for a frictionless pulley. Okay, now, any questions about that? Now I think the next part is we duplicate what we have over there. Yeah, so this is another salami of the same mass. And again, we neglect the mass of the spring spring scale compared to the salamis. Or salami. No one does that anymore. Okay, so what's the reading going to be? What do you think? What's your gut reaction? I'd like to know your gut reaction. The gut reaction is double, and you just almost know that that's probably not right. Is that right? So how do you think about this? What's a simple way of... Well, let me ask you something. Is this spring scale going to know any difference if I just replace this with a wall here? It's not going to know any difference. It can't tell. It can't tell. So the issue here gets back to the fact, I should have brought that spring scale in. It comes back to this fact that and this spring scale here, this graduator, you have something here that we can add that pulls. There's a spring in here, and there's an indicator. I'm having trouble here. And this, if you pull on this indicator, it's supposed to be an arrow, moves down here, right? And of course you have to counter, if you don't want this to accelerate, so you're going to have to exert an opposite force here. But that's irrelevant. We're just assuming that's fixed. And what the action that's occurring here is that we're stretching the spring. So it doesn't matter how you achieve this, you just want to keep it fixed. And you're going to have to exert an equal and opposite force, or it's going to accelerate. So it doesn't matter, that it's completely irrelevant if that this is, oh wow, it's just irrelevant. You can imagine putting, this is going to be the same as part B, or whatever it is. Yeah, part B. It's a good problem. Anybody have any questions about that? Yeah.
So, what would the spring read if it didn't actually, if you were bouncing out? Would we read double if it was actually able to measure like a dual spring that was able to measure weights on both sides?
I don't see how it can. If it was a dual spring.
Yeah.
Oh yeah. If you had, you can imagine you have two springs in there. You duplicate this, but going in the other direction. Right. Each of these is going to read mg. But that's going to be true, whether there's a salami here or not, you can replace it with a wall. It's going to be true here too. With your dual spring, you're going to be able to, basically what you've done is, we put a spring here, the spring scale. You can put another spring scale in here, but they do have a direction, right? There's a sort of an anchoring point, and there's this part that's going to stretch the spring. You would reverse it here. That's what you're saying. And you're just going to find the same tension. Has to be, because it's all in equilibrium. Any other questions or comments?
11 kilo salami is pretty big.
What?
An 11 kilo salami is pretty big.
Yeah, it's some salami. Okay, so the next one has to do, this is a practical thing. Do you guys know how they propel in deep space, how they propel spacecraft? There's different ways. Okay, there's different ways, right? And one of them that actually has been done, I read about this some years ago, is they have a radioactive source that kicks out particles. And the force, I looked into this because I had a thesis student and we were doing something related to that. The force is typical, like the weight of a piece of paper on Earth. But it's on, 24 hours a day, 7 days a week, and 365 days a year. And that little constant force just causes the acceleration to keep increasing. It causes the same acceleration, but the speed just keeps increasing. And if you wait long enough, it's going to be moving very fast. So, because there's essentially no drag out in space, right?
How do you put on those brakes?
Pardon me?
How do you put on those brakes?
You don't?
Yeah, that's a good question. I mean, you could, of course, reverse the direction of the propulsion, but then you're going to have to wait, years to slow it down, right? So that's one means. Here's another way. You've probably heard of this: is solar power. Light carries momentum.
So Bill Nye.
Yeah, so Bill Nye, the science guy. God, I can't watch that guy. And he's everywhere. You take look at an arbitrary picture of something to do with science, and somewhere in that picture you're going to see
There's
Bill
a
Nye.
picture of him out front here, There's a picture of him on the board.
What?
There's a picture of him right on the board out.
How did it? Well, yeah, okay. I hadn't seen that
He
one.
was here.
He was here?
Yeah, there's a picture of him right on the board with, I don't know if
God.
it's Dean or someone.
Okay, so did he do something on this? Or this?
Yeah, he's been testing a spacecraft with sails, basically.
Yeah. Yeah. Okay.
Could keep up with Bill Nye, I guess.
So light, and we haven't talked about momentum yet, but what we will, and I think it's reasonable once I use the word momentum, it's, if something, like a bullet or something has momentum, and if it hits and it gets absorbed, embedded in some object, it's going to exert a force over a brief amount of time. And we'll be able to calculate all this, but with the information here, we can do a calculation right now. So, because we're going to assume that this is the effect of these light waves here. 20 Newton force on this planar sheet here, perpendicular to the light, and it has this, and that's connected to some spacecraft. The total, and the mass is 900 kilograms. So, I don't know if this is realistic. I think this is probably an overestimate. I don't think it's very realistic, but it doesn't matter. It's the principle we're after here. So we have this force, relatively small for dealing with an object like this. We can find the acceleration. That's easy to do. It's millimeters per second squared. It's 22 millimeters, which is typically small by our standards. And we can find the distance that it goes. It looks like I did 24 hours there. Is that right?
How far will travel?
Yes, in 1 day.
Okay, so 1 Earth day. So I'm using 24 hours here. I'm just going to, I don't want to look this up. I just do the conversion. That's what I do. You can do it any way you want to, just do it right. Because I want to be able to cancel the time here, right? And come up with meters. And I come up with a lot of meters, and it's appropriate to specify it in kilometers. So it's a lot. It's roughly 100,000 kilometers in just 24 hours. I don't know if I believe this. I think it's probably, well, I think that's too high for typical values. We can put this, it's hard to appreciate a number like this, so it's natural to compare it to the radius of the Earth. So we can do a unit conversion here in the usual way. I didn't write that down here, but we can convert this to Earth radii, and we get 13 Earth radii. That gives you a feeling for how far it's going, assuming this constant force. What's the speed at the end, or the velocity at the end of the time interval, at the end of the 24 hours? Well, it starts from rest. This is constant acceleration, so we use our usual kinematics here. Simple formula. And we get about 2 kilometers per second. That's pretty fast. That's like railgun speed, right? Did we talk about this in this class, or was it the other one? Yeah, typical railgun speeds now. I think it's, around here, maybe 5 kilometers per second. Does anybody know? The Navy's working on this stuff. You guys know that?
Yes.
Yeah, I don't think it's deployed or whatever you say yet. Is it? Is anybody? Okay, yeah. But it's been, Gene did research on it. The professor here was here. And now Professor Alcaraz is doing research on it. So, yeah, if you're interested, see him. I don't know what, you guys are different, right? You're not combat system students, but there's a lot of flexibility in theses. If you're really interested in doing something, you can usually find a way. This is more like a normal university in that regard. So, you should do what you want. Do what you think is right for you. Any questions? Okay, so this is a simple problem, but it's a good one. We've got, it's practical. We've got a steady wind here. We want to have a small object. I can't get into fluid mechanics in this class, but in a typical case, if you set this up with this wind, it has some deflection here. Do you think that's going to be a constant angle? It's going to be fluctuating. And there's one word that's the cause of that, and it's bedeviled. I've never used that word before. Bedeviled people for centuries. It's called what? Turbulence, right? This is the thing that makes fluid mechanics really difficult, is turbulence. But if it's not moving sufficiently fast and this is small enough, you can actually get a steady, you can make this steady. That's what we're going to assume. There's a nice constant angle here. So we're given, this is on the surface of the Earth, we're given the mass, we're given the angle. We can, I guess I should look at the problem again. Find the push magnitude. This is the force of the wind on the mass and the tension in the cord. Okay, so here's the diagram, right? We have a picture, some kind of picture. Let me call it a picture or sketch of something that's going on. The next thing is we draw a force diagram. We isolate the body here and draw all the forces on the body. There's going to be the force of the wind that's horizontal. There's going to be a tension in the cord here, pointing directly opposite this cord right here. And there's going to be the weight. We've got these three forces. And they have to sum to what? 0, because it's in equilibrium. And we have two directions here. This is a two-dimensional problem. So if I look in the x direction, this force has to be balanced by this component, the x component of the tension, which is the same as this. So it's going to be next step. Picture force diagram, Newton's second law. In the x direction, here is. Now I'm not going to write F is equal to ma here. There's no a. So what I do is write the force balance. You can do it any way you want to. But I know I can see this pointing this way and that pointing that way, and they got a balance. So I'm going to write it like this. This tells me there's 0 net force. But you can do it any way you want to. You can write it as mg, an alternative in the x direction. Wait, I went vertical here. Sorry. I went vertical first. Let's look at horizontal here. We're going to call that the positive direction. I can write that. The net force in the x direction is 0. But you can see that it's equivalent to this. Right? Any way you want to do it, as long as it's right. Here's this is the x direction. Here's the y direction. It's similar, right? And now we got two equations here. How many unknowns? What are the unknowns here? We don't know the tension. What else? We don't know the force of the wind. So we have two equations and two unknowns, and they're linear. You don't see any t squareds or f squareds or the square root. So this is we're going to be able to solve this. And the simplest way to do it is to note that there's just one unknown here. We might as well calculate it. Solve for the tension. We get it's weak here because this is tiny. It's very light. We get 3.7 millinewtons. Once we've got the tension, we can then substitute the value in here and find the force of the wind, and it's 2.2 millinewtons. Those are the magnitudes. The directions are given here. Okay, any question about that one? It's simple, but you want to make sure you understand stuff like this. Here's this problem has acceleration. Now this will look familiar to you. What did we solve in class? Do you remember? We solved the classic problem in class where the surface there that M1 rests on okay, so we solved this in class. So this is actually a generalization of what we did in class. We're now going to incline the surface by some amount. So we're going to actually get definite, we've been given definite numbers here. But I want to make sure you recognize something here. Suppose we know these, but suppose we don't substitute the values. We just proceed purely algebraically. We're going to end up with a formula for the acceleration and the tension. I guess that's what we want to find here, is the acceleration and the tension. We're going to end up with a formula. How do we check that formula? When you got a formula, there's always going to be special cases. What is one special case? How about theta equals 0, right? That's this. So you want to recognize that. Standard thing that people do, especially in research, is you want to check in special cases. Now, but that's not what's really interesting here. What's really interesting here is which way is this thing going to accelerate? Or is it just going to have no acceleration? This is a frictionless surface, right? Is it going to go clockwise or counterclockwise? Is it going to go that way? Is this going to accelerate downward, or is this going to accelerate along there? This been going up. Can anybody tell by looking at that? Well, if the masses were the same, what would happen?
The same.
This force is going to be bigger than the force here, right? Because what's relevant is this component of force. It's going to go this one's going to go down. Excuse me. If the masses were the same. If this mass were greater, this is obviously going to go. But if this mass were greater, now we have competing effects, right? So I don't think it's obvious. because it is greater. I don't think it's obvious which way it's going to go. So how do we solve this problem? Well, here's a simple way to do it. Let's assign a positive direction. Let's suppose that this is going to accelerate downward, have positive acceleration downward. Let's just suppose. We go through the problem, solve for the acceleration, being careful with all the signs, of course. If we get a negative sign for the acceleration, what does that tell us? It's going that way, yeah. This is accelerating upward. So that's how we do it. Simple. And that's what we're going to do here. We're going to take, I think I took positive downward, yeah. So essentially we're going to pretend like it's accelerating this way. But if it's not, the mass will be able to handle it. It can handle both ways. It'll tell us it'll have a minus sign. The acceleration will have a minus sign, telling us that this is actually accelerating upward and this is accelerating down there. Okay, so there's the picture. Now we have two force diagrams because we have two bodies. That was really one of the points behind doing this problem in class. And here's the one on the incline. Okay, so here's the incline, same angle here. I resolve. What's relevant here is the component, the acceleration is going to be in this direction. So I'm going to choose, for this one, I'm going to choose this to be like the y-axis and this the x-axis for this mass. I need to resolve gravity into two components, perpendicular to the surface and parallel to the surface. So this is going to be m1g times the cosine of theta. There's a right triangle here. This is going to be m1g times the sine of theta. Now n is perpendicular to the surface. T is parallel. So I'm done with that, okay, with the force diagram. And now I write down Newton's second law. What's happening perpendicular to the surface? What's got to be true? There's no acceleration. So these forces have to balance. I didn't even write that down. That all that is tells us what the normal force is, and we don't care in this problem. I didn't even write it down. This is the relevant direction here, and this is the positive direction. You got to be careful about this. So I'm going to write t minus m1g sine theta is equal to m1 times a. I'm not writing m1g sine theta minus t, am I? I'm doing it. I have to choose this direction because this is in the positive direction. What we're calling the positive direction. This is in the negative direction. So you have to be careful there. Now, this is easy. We just have the same tension. The pulley just redirects the tension force here. We got T and M2G. And again, I'm choosing down as positive, so I write M2G minus T is equal to M2A. We've got two equations in two unknowns, two linear equations, the tension and the acceleration. And the simplest way to do here is just to add the left sides and add the right sides. The tension cancels here, and we get this equation when we add them. And we actually could have written that down right in the beginning. That's the trick that I mentioned that I should not have, so don't do that. In fact, the way, I just realized something. The way I'm going to present that in the lecture notes, and I may have forgotten, we can view that as a check on our solution. Do you guys remember that, how we sort of rectilinearize the problem here? Let's not talk about it. Forget it. This is the proper way to do the problem, okay? And the quickest way to get at the answer is add the left sides, and we get this. So we can solve for the acceleration, right? Just bring this over here. We get a number. And is the acceleration positive or negative?
Positive.
So what does that mean?
It's going down.
Yeah, it's going down. Now, it could have been going the other way. There's nothing wrong with that. It just happens to be going down. And we don't know until we solve the problem. Finally, we get the tension. Once we know A, we can use either equation here. I happen to use this one. Once we know acceleration, we have one equation and one unknown. We can get the tension. And we get that. Okay, got the idea? This is, yeah.
Let's go over a little bit more about setting up the first force diagram with M1G. I'm just.
So this one?
Right.
So we want to draw all the forces on this mass. There's a tension force along the incline,
Yeah.
right, which we're going to call the x direction for this. That's the relevant. There's a perpendicular force. We're assuming no friction, but there is that normal force. It's always perpendicular to the surface. That's got to be perpendicular. That's a right triangle right there. And then we have, so when I draw this, I don't have these, I have this. And then I say, oh, I want to resolve this into these two components. So I strike it out. I replace it with these two vectors. So now I see that this has to balance because there's no acceleration in that direction. And then this minus that is going to give us the mass times the acceleration in that direction.
Because it's the resultant force.
Yep, the net, Newton's second law, the net force is the mass times the acceleration in any direction. Choosing the direction to be here, that's what's relevant here. Here it's vertical direction. Any other questions? Okay, this is a great problem. So, and you guys may be familiar with this this might be on ships. It's called a bosun's chair, something like that. Sounds like Navy stuff to me. I wouldn't know.
Sailboat.
Pardon?
We have sailboat.
Oh, sailboat. Okay.
We have dumbwaiters that are very similar.
So it says, this is what says it all. Somebody's sitting in this chair type thing here, connected fully, and the person's pulling down. Okay? With what has to be the tension? With what force? The tension here is the force exerted by the person. Force exerted by the person. So what has to be the, maybe I better look at the question is, what is the force here? And we're going to assume that the person's rising at constant velocity. So that this is the picture. The force diagram on the all that's important here is the total mass of the person in the chair. We're just going to call that M. So that's the body that we're talking about here. And we have to draw all the forces on that body. There's a weight downward. But now if you look at this, if you look at the forces on this body here, on this object here, there's a tension force here. Okay, well, again, we neglect the mass here. The tension force just gets transmitted. There's also, where the person's holding, there's an upward tension force. You can't deny it. It's there. So the force diagram actually looks like this. We're letting T be the tension in the cord, and there's two forces. So what does this mean? If there's no acceleration, these forces balance, and it means that the tension that you have to exert is half the weight. If somebody were doing this on the ground, suppose this person weren't holding that and somebody was pulling on the ground, with what force do they have to exert? What tension do they have to create? In other words, what force do they have to exert downward to get the object to move with constant velocity? mg. Now, most people, including me, when they see this, they go, wow, this kid, it seems like something's wrong here, right? Because it looks like this, how can we do that? It seems like it's too easy. Well, what's bothering you, but you don't know it now, is something called conservation of energy. And we'll talk about this if I need to remember to bring this up in the future. But let me just tell you the answer here. When I wrote it it's not on here. Suppose a person rises a certain height. A certain amount of work is going to have to be done, and we will carefully define work. Okay? If instead of this person pulling on the rope, somebody down there, they have to exert twice the force, but they pull the rope through half the distance. To get this to rise a certain height, the person has to pull on the rope through twice that distance. So the works are the same. Both people expend the same amount of energy to raise this object here a certain height. There is no violation of conservation of energy. And no one's ever found a violation of conservation, as we will discuss. Anyway, hold on, we'll talk about this. But it's entirely true. In fact, with a so-called block and tackle here, with a number of pulleys, you can reduce that force down to a very small value, right? The standard example is somebody lifting an engine block. You know, people can lift an engine block. Well, they used to. Nowadays, it's all power, you know, right? And we pay for it. The customer pays. That's another thing I don't want to get into. So, but a person could lift an engine block. Has anyone ever done this or seen it?
Yes.
And what you'll see is this person just keeps pulling this chain and pulling this chain, and it slowly rises a very small amount. Okay, so we'll get into this when we get into energy conservation. We've got, we're out of time. We've got one more problem here. It's 89. So in this problem, I'm going to look at this from two different points of view. This is a spaceship on the moon. And it's taking off with an acceleration of 1 meter per second squared. So I'm here on the moon. I measure 1 meter per second squared. The moon has this gravitational field. It's roughly 1/6 on the Earth. And the weight of the person on Earth is 735 newtons. All right? And I think the person's on a scale here. Is that right? Okay. So I want you to imagine, it doesn't say so. Imagine that the person is on a scale here. What we want to find is the force of the spaceship on the person, the normal force. That's going to be what the scale reads. Scale reads that force, as we discussed in class. So this person sees this picture, writes down this force diagram. The person has mass m. There's some normal force, is what we're after. And there's the force of the moon. And Newton's second law gives you this equation. We can solve for the normal force, because that's what we're after. And you'll notice I knew some algebra here, and there's a reason for that. I can factor out the m, plug in the numbers, and I'm going to get a value. Okay? Now, the interesting thing here, so that's fine, just straightforward. This is actually pretty straightforward, Newton's second law. There's another way of doing it. You can go to the frame of reference of the person in the spaceship. Now, that's not an inertial frame, so you have to be careful. But the way you can do that is, if this person is accelerating upward with acceleration of this, there's going to be an effective gravitational field in there that's going to be given by what the moon is, plus you got to add 1 to it because of that upward acceleration. Remember we talked about that in class? So if this spaceship were accelerating upward at this amount, in your frame of reference here, you would feel a gravitational field of twice, 3.2 meters per second squared would be the acceleration due to gravity. So you can, I just want to point out, you're not asked to do this, but you can solve this in the frame of the spaceship. Even though it's not an inertial frame, you just have to do this effective gravitational field that we discussed a little bit in lecture. And you get the same answer. You get the same answer. Any quick questions on that one? Okay, so tomorrow we get into the second chapter on dynamics.